Okay, so let's begin. So as I said right from the beginning, in today's class, what we are doing is that we are going to get into resistance. But in this case, when we are talking about resistance, what we are going to study is like some technical terms. And it says here on this PowerPoint that this is on page 81. Actually, that's from another book, which is called DC Fundamentals. That, I mean, but don't worry like about that page 81. So what really matters is what we have on Conestoga already. Okay, and all those technical terms that the book refers to, all those technical terms that we are going to cover in this lesson anyways. So one of the classifications that tend to happen, in the field, conductors are classified like in three different types. So not conductors, but materials are classified in three different types. We either have conductors, good conductors, like in the case of copper and aluminum. We have pole conductors, like in the case of semiconductors, and then we have insulators.
That looks awesome.
Pardon me?
Did your mom share the same perfume or what?
Yeah.
Okay, so I can hear some guys chatting about something else. So just, okay, just keep it quiet, please. So anyways, like what's the difference between a good conductor, a pole conductor, and an insulator? Do we know the answer to that question? What's the difference between good conductors, poor conductors, and insulators? What's the difference between them? What makes a material either a conductor, a semiconductor, or an insulator?
The amount of valence electrons in the outer shell.
Perfect. That is correct. Thanks, William. Okay, and then the next thing is that we are going to get into the four factors that determine the amount of resistance in a wire, okay? And we are going to see a formula for those four factors that is going to explain in this formula, like all these things that constitute the amount of resistance that we are going to have in a wire. Okay. So there's something which is called conductivity and resistivity. Conductivity, the ability of that a conductor has, that a material has, to allow the easy flow of current. In this case, in our case, electrons. And resistivity, the ability in this case that the conductor has to oppose to the flow of current. Okay, so we are going to be using an equation today. Which is that R, meaning resistivity, is equal to K, and K is going to be a constant factor that we are going to find in a table that I'm going to show you later today. And then it's going to be equal to K times Joule current divided by the area. And that's going to be the first aspect that we are going to cover in this class. What is that area that we are talking about? Okay, so we'll have to delve into what is called circular mills, and then we'll see why is it that right after we have a 4-up conductor in table 1 to 4 in the code book, then we have all these KCM values, for conductors. Also, like, okay. So we're not going to be using the color code. That's something that you did in electronics. But of course, we are going to use the American wire gauge, and we are going to see it in the table that we are going to use in today's class. And if you might wonder, like if you are going to be using that table for the test, by all means, okay? Like you can use any tables you want. And of course, I guess that when you are doing your test, you are using all the information that you had available. So let's get moving. Okay, so this is just redundant. Okay, so good conductor allow the easy flow of current. I mean, non-good conductors or insulators, they prevent the flow of current. And I mean, whenever we have between 1 to 3 electrons in the valence shell, then we know that we are going to have a good conductor, like in the case of copper and aluminum. Now, when we have, sorry, okay, so when we have between 7 to 8 electrons in the valence shell, then we know that in this case, we are going to have an insulator. Now, let me warn you that there's no any insulator which is perfect, okay? And the reason to that is because with enough pressure, we would be able to pretty much push any current through an insulator, okay? So that's why that all insulators have a voltage rating, like in the case of NMD90, which is the wire that we use for residential construction. The maximum voltage rating of that wire is 300 volts to ground, while like in the case of T90 nylon, you have 600 volts, right? When you have underground wires like TWU, then you have a voltage rating that goes all the way up to 1,000 volts. So, and the reason why you have different voltage rating, because each insulation have a different chemical composition in order to prevent the flow of current through it, okay? So as I said, there's no perfect insulator, and given enough voltage, which is the pressure that pushes the electron through a conductor, I mean, given enough pressures, we'll have a flow of current, okay? So that would cause what is called insulation breakdown. And then between the two, between conductors and insulators, then we have the semiconductors. And I hope that in electronics, you learned that, I mean, that semiconductor that has 4 valence electrons is silicon. And that silicon is the most widely used semiconductors in the field of electronics. Let's keep moving then, guys. That being said then, we are going to have the ability to use different materials or to see different materials and explore the resistivity of this material and how is it that your resistance in your conductor is going to depend, number one, on the type of material, the material that is made of. It's not a secret that, like in the case of copper, well, if we go to table 1 to 4 in the code book, we are going to find that the minimum size copper conductor that we had available there is number 14, okay? And that one have an amp rating, which is equal to how many amps? Do you remember? For 60 Celsius, you have an amp rating, which is equal to 15 amps, right? Now, if we, on the flip side, and that is copper, on the flip side, if we look at aluminum conductor, the minimum conductor size for aluminum as per table, as per table 3, or table 4 in this case. I'm gonna use table 4 in this case, you know. Correct me if I'm wrong. The last time I saw it, I recall for number 12 aluminum being 15 amps also at 60 Celsius. So in both cases, you can see that number 14, American wire gauge copper, it is thinner conductor than number 12 aluminum. However, both of them have the same ampacity. Why is that? That's because copper is a better conductor than aluminum. And we're gonna be surprised because copper have only 1 valence electron, while aluminum has 3 valence electron. And I only said that because just to emphasize the fact that the type of material is going to determine how much resistivity we have in the conductor. Also, the other factor will be the length of the conductor. The longer the conductor, the more resistance that we are going to have in the conductor. And that's why that you have that table, which is table D3 and table D4 in the code book, that allows you to determine the voltage drop that you are going to experience in a conductor at 120 volts and 1% voltage drop, okay? But that's something for code. On the other hand, also the sectional area, which is, in other words, the gauge of the conductor, that's going to determine the, that's going to determine also the ampacity of the conductor. And the last one is going to be your temperature, and that's why you have table 5A, okay? In table 5A, in the code book, then you have the temperature correction factor that allows you to calculate what's going to be the maximum length that you can run a conductor under, once you have a temperature above 30 Celsius. In our case, we are going to be using 20 Celsius as as a temperature factor, as a temperature rating. Any questions so far? So let's get moving, guys. So just give me 1 second here, please.
Yeah, of course.
Anybody have any question?
Yeah, I do, Greg. Is there anything in another book that we have that we can follow along with you instead of, I know this is out of material from another book or another source, but is there anything else that we can follow along with similar resources?
Okay, so this is, as I mentioned, this is from another book. So as I remember, like, posting this in the past, let me just give me 1 second there. So would you like to have like the PDF document, I guess, right? Of this PowerPoint.
Yeah, that'd be good.
Yeah, sure, that works. Or even give us another chapter we could read or something like that, or look up into with one of the books that we already have currently.
Okay, just give me 1 second there, please. Yeah, I could, I could upload that chapter. So just give me like a couple minutes to put that PowerPoint online, okay?
Perfect, thank you.
You're welcome. Okay, guys, so I just posted online a PDF document, which is called Resistivity of Materials. So now you should be able to open that chapter 7. In spite of that, like, I'm going to check, what else I had available, because that book, I have it in the college, and usually, like in the past, I have given physical copies to the students, but because we are not in the college, like I never uploaded this online, like this type of additional material. Okay, so we only use this. We only use this material just to, to expand the all the information that we have in Delmars. Okay, so were you able to open it?
Yeah, I have it now. I opened it.
Okay, perfect. Okay, so let's keep moving, guys. So as I was saying, like in the case of, we already covered that resistivity, the resistivity of the material is going to be depending on 4 different factors. Now, one of these factors is going to be the K. Okay, so, and the K, which is the constant that we are going to use in the formula that we saw previously, okay, that formula, that K factor is going to be depending on the type of material, or the material from which the conductor is made of. Now, in order to start understanding where that concept of circular mills comes from, we have to look at the resistivity in the English system, okay? In the English system, we have something which is called the mill foot. And you may wonder, so what is the mill foot? I'm gonna show you that a mill, okay, like if we have 1 inch, if we take 1 inch, 1 inch usually, if we are going to use a tape measure, 1 inch is divided on a tape measure into how many parts? One inch is divided into how many parts on a tape measure, on a ruler?
Honestly, depends on what you're looking at. They can all be different.
Pardon me?
It could
Standard
be
16.
In 16 parts. Perfect. So like all of you, like in the field, like if you take like a 1/2 inch conduit, which is a 60 millimeter conduit, I mean like 1/2 inch conduit, 3/4 inch conduit, 1 inch in all, out there in the construction industry, it is divided in 16 inches. Oh, excuse me, in 16 spaces. So all the way down from, okay, all the way down from 1/16 of an inch, all the way up to 16/16, which is in reality 1 inch, right? Now, in the case of resistivity material, in the case of the mill foot, we have one mill foot when in a conductor, we have the gauge, the thickness of 1 mil, okay? And then we have the length of 1 foot. So when you have that, okay, let me take it back here. So when we have a conductor, when we have those 2 parameters, then we have found our K factor, we have found the natural resistivity at 20 Celsius for a given material, like in this case, copper or aluminum. Now, I began by telling you about like how many spaces 1 inch is divided, because I want to bring to your attention that in the case of the mill foot, 1 inch is divided into 1,000 equal pieces, okay? So in other words, whenever we have 1 divided by 1,000, that's going to be equal to 1 mil, okay? 1 mil diameter. That's a very minute unit. Now, if we take that conductor that had a gauge of a thousandth, of a thousandth of an inch, okay? And then if we take a foot of that material and we measure the resistance of that material, we have found the K factor for that material, which is going to be a constant at 20 Celsius. So I just want to take you to this next slide, because like in this instance, we can determine them what's going to be the pretty much like the cross-sectional area of a conductor if we use the formula in order to find the area of a conductor, okay? So in this case, we have to keep in mind that the thicker the wire, of course, the lower that is going to be its resistance. And when the wire gets thinner, then we are going to have a higher resistance, okay? So in this instance, like we have like in this circle that we have 0.001 inch. So when we have 0.001 inch, then we have 1 mil of cross-sectional of the cross-sectional measurement, okay? So in this case, the diameter for this conductor, for this circle, is going to be equal to 1 mil, which is 0.001 inches. So let me take you to this example here, okay? Let me do the following. I'm just going to, okay, let me see. I'm just going to do it right here. Okay. So what I want to show you guys is, if I want to determine the area of a circle, we have that area is going to be equal to r squared, okay? Well, it's going to be equal to pi times r squared. Also, we have that r, which is the radius, is going to be equal to d divided by 2. So in this instance, if we are going to be using the mil as our unit, and we say that we have 1 mil of diameter in this circle, then, well, actually, how much is the radius? That's going to be 1 mil divided by 2, which is going to be equal to 0.5 mil of diameter. Okay, so we have 0.5 mil diameter. So now we take our radius, our pi, excuse me, which is going to be equal to 3.1416. And when we multiply that by the square of the radius, or radius square, like in your case, that's going to be equal to how much? Can you do the calculation pretty quickly to find out, please?
It's 0.785.
Perfect. That's going to be equal to 0.785 what?
Mil.
And this, in this case, it's going to be a square mils because it's area, right? Now, from here on and going forward, the reason why I was doing this calculation is because I want you to understand that whenever we have the diameter of 1 mil in a conductor, and I mean, in reality, the amount of square mils that we are going to have in the whole conductor is going to be equal to 0.7854 square mils. Okay, now from here on, I want you to keep in mind that every time that we say that we have 0.7854 square mils, we are going to come up with a new unit that we are going to call circular mil. Okay, so every time that we have an area that is equal to 0.7854 square mils, that will be equal to 1 circular mil, which is going to be the unit of area that we are going to use going forward. Okay, so to simplify things, what is done in the field is that if you want to find the amount of circular mils that you have in a conductor, you say that circular mils is equal to diameter square. Like if you went to do and backtrack all the calculation, you would find out that this formula always works. The circular meals will always be equal to diameter squared. Okay, so that means, okay, now going into the next slide, that means that if we have a conductor that is ½ inch in diameter, we take a caliper, a vernier caliper, and we measure that we have a diameter which is equal to ½ inch. That means that we have, of course, ½ inch is equal to 500 mils. If we have 500 mils, because I already told you that diameter square is going to be equal to circular mils, if I square my 500 mils, that's going to be equal to 250,000 circular mils. Usually you would see this as 250 kcm. Okay, so a 250 kcm conductor name, it's equal to a conductor that have a diameter of ½ an inch. Are you okay with this so far?
Yeah.
Okay, so let's keep going, guys. Now that we know where, I mean, like how we are going to use, how we are going to determine the area of a conductor, now we can jump into this formula. In order to use this formula, we are going to have to keep in mind that, well, we are going to have to use a K factor, and you may wonder, so what is that K factor? Where are we going to find that constant, that number? Because I'm pretty sure that probably you don't really want to be taking like 1 mil by 1 foot in length in order to try to determine how much resistance you have. So in this instance, what you are going to do is that on Iconestoga, I uploaded a table here. So you go under week 7, under a folder, the wire tables and sizing conductors folder. Right on number 5, that's topic number 5, that's just a table. So when you click there, you are going to find this table. And on this table, you have the gauge of all the different wires that you are going to play with. And you can see that the gauge begin at 4.0 all the way down, all the way down to 44, okay, to number 44. So the only conductors that we tend to use usually, you know, in the field, like in our case, is like 14 and above, okay? However, just be aware that there's a lot of stuff out there, you know, like coils, relays, solenoids. There's a bunch of stuff that use very, very small conductors. And also a lot of small transformers, motors. There's a lot of stuff that use small currents and small conductors, okay? In our case, we are going to be using this table just for basic voltage drop calculation. Let's say, like if we have a number 14 conductor, which is very common, okay, we would be able to find here under this column the amount of diameter, the diameter in mils. For a number 14, it's going to be 64 mils. And that's going to give you an area which is equal to 4,107 circular mils. So whenever we are using this formula, okay, whenever we are using the formula that says that R is equal to K times L divided by A, and I'm going to go back to that formula so you can see it once more. Whenever we are using that formula, guys, that A corresponds to a number right here, depending on what is the gauge of the wire that you want to use. Okay, so now you, as I was saying before, you may wonder, okay, so where is it that I'm going to find that K factor? So when we scroll down on this table, you are going to see right here at the bottom that we had a bunch of conducting materials. In our case, we are going to concentrate on copper. That is going to give us a K factor, okay, the Millfoot K factor, which is equal to 10.4. So in that case, we have 10.4 what? Ohms per Millfoot. In the case of silver, no silver, we're not going to use silver mostly. We're going to use aluminum. Like in the case of aluminum, we can see that the amount of ohms per Millfoot is going to be equal to 17. And depending on the material type, okay, we are going to have different K factors. So this side of the table is going to be Folger K. Please keep that in mind. That's your K right there. Right here is your K. And right on the top, right here. Okay, so that's going to be your A, your area right there. That's going to be your area, your A, okay? Now, I'm going to give you an example on how to use the formula in just a bit. So I'm going to go back and stop the screen here so we can go back to our PowerPoint. So let's say then, now that you know where you are going to be getting your K and your A, let's say the following. Let's say that we have the following condition. Let's say that we want to find the resistance that a given wire has. Let's say that this wire is made of copper. Okay, so if that is made of copper, the K factor is going to be equal to 10.4. And we are going to use, let's say that we have 20 amps. Okay, so that I here stands for, that L here stands for the length in feet. Okay, so I'm not going to get into the 20 amps. Sorry, guys. So let's say that here we have 100 feet. Okay, so now we want to know, like, and let's use an number 14 conductor. Let's say that we have a number 14 conductor. So if I go back to the table, a number 14 conductor would give me, that would be equal to 4,107 circular mils. Now that we have that information, then we would be able to determine how much is going to be the resistance of that wire. So what is what is that I'm talking about? I'm talking about a copper conductor. Okay, they have a length of 100 foot. And they have a gauge of number 14 conductor. Okay, so in that instance, let me do the calculation pretty quickly. So that would give that give me, like in my case, in my calculation, I have that we get a resistance which is equal to 0.253 ohms. And you may wonder, so okay, sure, I found the resistivity, I found the resistance of that wire. So what? With that information, you are going to be able to apply Ohm's law and determine how much is going to be the voltage drop through that conductor. So in this case, we have that EV, which is voltage drop. Okay, and how do I get this EV? By using Ohm's law. In Ohm's law, we have that E, which is electromotive force or voltage, is equal to I times R. So let's say that now my I is equal to 20 amps. And I know you might be saying, wait a second, you cannot put 20 amps on a number 14 conductors, but table 1 in the code book at 90 Celsius actually says yes, that you can do that, okay? But you can put 25 amps, no problems. So, and we are doing this for calculation purpose. Okay, so I'm gonna be putting 20 amps on this conductor, and with the resistance, which is equal to 0.2532 ohms, I would be able to determine how much is going to be the voltage drop that I'm going to have on that conductor. Keep in mind that the voltage drop is going to be based on the fact that I have 20 amps, number one, and number two, that I have 100 foot of a number 14 conductor. So in this instance, I had a voltage drop which is equal to 5.064 volts. Now, I want you to notice something about this as well. Like in this case, I want you to notice that that's only the voltage drop that we experience in one of the conductors, okay? So in this case, if I have a circuit, a branch circuit, and right here, I have a switch. If that wire that extends 100 foot from the panel, or from the feeder, is going to be feeding a motor, remember that this is going to be the hot, and on the hot conductor, that I'm going to call the hot just as a custom, or line one, it needs to return back through the neutral to the panel again, okay? So in this case, we have line one in neutral, and if we have 5 volts drop on the hot, how much voltage drop do we have on the neutral? Is it going to be 5 volts as well? Let me tell you that yes, indeed. Because if we have 20 amps going this way, 20 amps has to come back this way. If we had 100 foot on line one to the motor, we had 100 foot on the neutral getting back to the panel. So you might as well, I mean, get into the habit for calculation purpose, for calculation purpose, that whenever you do a branch circuit, you always have to multiply your voltage drop times 2 in order to determine the total voltage drop that you are going to have in the wire, like in the circuit that you are going to install, which in this case would be 10.128 volts. Any questions about that? For those guys that just joined us, I'm going to be posting this video online sometime tomorrow. So, I mean, whatever you missed from the start of this class, then you are going to be able to see it anyways.
Oh, my internet just went down. I was here at the beginning of the class.
Oh, you will hear at the beginning. Perfect. Anyways, any questions so far, guys, from what I told you, from all these voltage drop stuff?
I think it's pretty straightforward.
Perfect. I'm glad to hear that. Now, I don't want to, so what I'm going to show you next is that, okay, so I'm going to be sharing another screen with you. So I already showed you like how to find your K, how to find your A and your K on this table. Now, just for the sake of clarity, okay, make sure, please, that you review the resistivity of materials, the PowerPoint, and then you are going to be doing later on, not today, anytime you want, from now to the weekend or to next week, the wire tables and sizing of conductors. So you have like a small quiz to do there. And then there's an important, I mean, all these handouts, thank goodness, have an answer key. So you are going to start by doing your, like filling out all these handouts. And you can always go back and check the answer key to see if everything looks good, if everything is good with you. And then it's supremely important that you start to play with this, you know. Okay. Okay. I started with this question. Getting back to this, okay? So if you needed to find, like I show you like a few different formulas, but if you needed to find the diameter of a conductor with a cross-sectional area of 10,380 circular mils, so in that case, we are gonna take the area of the conductor. We already know how many circular mils we have. So we would be taking a formula that says that diameter squared is equal to circular mils, and use that formula in order to find the diameter of the conductor. Okay, so in that case, we have that the diameter would be equal to, okay, like this is an exponent. It will go to the other side of that equal sign, performing the inverse operation. And the inverse operation of that exponent is a square root. So when we get the square root of circular mils, then we're going to be able to get the diameter in mils. Okay, now if you needed to have that diameter in inches, then all you have to do is to divide your mils by 1,000, and then you'll get it in inches. Okay, so something else, as you continue to explore all this stuff that I have posted online for you, you are gonna get into this topic. Okay, so give me 1 second here. This one. Okay, so what is the effect of temperature on your conductors? Usually this is a topic that it takes 2 hours to go through in the college when we are doing class like right there. So what I'm gonna be doing for this topic is that I'm gonna be posting a video that I found on YouTube. And then, like, if you happen to have any questions about this, just let me know. Like in this instance, we have 2 different formulas that we are going to be using. These are with an upward arrow means the amount of resistance increase. The resistance increase is going to be equal to RO, which is the resistance, the original resistance of the conductor. And then we have this alpha, and you may wonder again, so where do I find that alpha factor? In order to find this alpha factor from this handout, you are going to go back to table 5. And on table 5, okay, we have here that delta, which is the temperature coefficient that indicates how much will the resistance change in a conductor according to the temperature increased. So in this case, like if you are going to be using copper, so your alpha factor for copper is going to be 0.0039. For aluminum, it's going to be 0.004. And when we go back and we apply, like, okay, let's keep in mind that we have the 0.0039 for copper. So let's go back here. So when we are going to apply this formula, then we would be using that 0.0039 for the alpha right there. This delta T indicates the change in temperature in Celsius. Oftentimes you might wonder, so how do I find delta T? Okay, so delta T is going to be the change in temperature. So delta T, let's say that we have a conductor that went from 20 Celsius, the temperature increased to 40 Celsius. So what you have to find in this case is how much is my delta T? My delta T is gonna be R40 minus 20 because you just want to see how much has the temperature changed, okay? So in that instance, that's gonna be equal, of course, to a change of 20 Celsius. So in here, you would be using your 20 Celsius. In here, you would be using your 0.0039. And here, you would be using the original resistance of the conductor. Let's say that the original resistance of the conductor, let's say it was 2 ohms. If that was 2 ohms, and you want to see how much has the temperature the resistance have increased, in that instance, we would be doing the following. We would be saying, well, I have 2 times 0.0039 times 20. So my resistance have increased by 0.156 ohms. Okay, now that we know that the resistance have increased by 0.156 ohms when it goes from 20 Celsius, okay, when it goes to from 20 Celsius to 40 Celsius, now with the second formula that we have right here at the bottom, we would be able to determine the total resistance of the old conductor. So you can see that right at the beginning, my initial resistance, which is the original resistance of the conductor, as we can see in here, I said that it was 2 ohms. Okay. And the increase of resistance was equal to my 0.156 So that would give you a total increase, which is equal, a total resistance, which is equal to 2.156. That means that if we have a conductor, which is made of copper, and the conductor changes from 20 Celsius to 40 Celsius, the resistance will increase from 2 ohms, like in this initial case, to 2.156 ohms. And that's how you use these two formulas in order to determine the increase in temperature that you are going to experience when, the increase in resistance that you are going to experience whenever you have an increase in temperature. By the same token, of course, if the temperature decreases, then we're going to have less resistance. Any questions about this?
Yeah, where'd you get your 2 ohm at the start?
Let me see. Excuse me. Let me up my volume a little bit. Say it again.
The 2 ohm you had that. Where did you find that again?
Well, did I get the 2 ohms from?
Yeah.
That was just a made-up number, just to show you how to use it, okay?
Okay.
So like if you wanted to calculate this original resistance, right? And right from the beginning, that RO, that original resistance, is gonna be what? In that case, it's gonna be K times L divided by A. That's how you find the original resistance in any other problems. Because K is gonna be the type of material, okay? Either copper or aluminum for the most part, the length of the material, and then the cross-sectional area of the material. So that will give you that RO. If you want to be more thorough, more specific. So in the case of the 2 ohms that I was using, it was just, I just supposed that I have a conductor with an initial resistance of 2 ohms. And I departed from that point of view. Okay, guys, so I'm just hoping that, well, we're getting very close to the end of this course. And for this week, I'm just hoping that you are gonna go ahead, and finish. Okay, so just these 2 handouts. I'm pretty much just giving you 2 handouts. There's an additional one, which is number 1. So just take the time and fill it in as, I mean, if you can. And I'm pretty sure you can. I mean, what I'm saying is time permitting. So try to complete handout number 1, number 2, and number 3, and take a look at this number 3 where the handout, okay? Then this one is going to be very, very important to do. Number 4, but number 4, I mean, if you have been able to do like 1 to 3, then number 4 is not going to be so hard to do as well. Okay, and that's based more on voltage drop, you know, and determining what's going to be the length of the wire that I can use if I have. And then next week, we should be touching on magnetism, but what we are going to be doing next week is that we are going to take the time to review anything that you want to review from this course before you do the final exam on the 18th of December.